All right, let's pull back the curtain on the future of flight. We're diving deep into the engineering spec for eVTOL hybrid propulsion systems. Now, these aircraft, they're poised to completely change how we think about our cities. But getting them off the ground and certified, well, that's one of the most intense engineering challenges on the planet.
So here's how we're going to frame this whole thing using a classic top-down approach. Let's call it situation, complication, and resolution. The situation. We have this amazing new era of advanced air mobility, but, and it's a big but, batteries alone just don't have the juice for commercially viable flights. The complication. Okay, so we use a hybrid system. The problem is, that system is incredibly complex and it has to be certified to the exact same safety standard as a commercial airliner. The resolution. There's only one way forward. We have to apply a rigorous aerospace-grade engineering process. And let me be clear, this isn't a choice. It is a non-negotiable requirement to even get in the game.
So, here's our flight plan for today. First, we're going to nail down exactly what this range problem is. Then, we'll architect the solution, the P13 hybrid system, and see how it operates in its 4 different modes. After that, we'll get into the philosophy behind development, the non-negotiables. We'll quantify what safety really means. And finally, we'll walk through the absolute gauntlet of testing required to prove it.
Okay, let's get right to the heart of the problem. Why can't we just, slap some bigger batteries on these things and call it a day? Because the entire industry is running headfirst into a hard wall of physics.
It all comes down to this number right here, 280 watt-hours per kilogram. That's pretty much the ceiling for the best batteries we can make today. Now, in an aircraft where every single gram matters, this number isn't just a hurdle, it's a brick wall. It means pure electric designs are stuck doing short, cross-town hops, not building a real, profitable transportation network.
So how do you solve that massive energy problem while still keeping flights over our cities clean and quiet? This brings us to the beauty of the P13 hybrid systems architecture. Take a look at this. This is the P13 architecture at its core. What you're looking at are 2 totally separate highways for power. One is purely mechanical, right from the engine to the propeller. The other is all electric, flowing through that high-voltage bus. This dual-path system is the secret sauce. It's what gives it range, and more importantly, it's the foundation of its safety.
So let's break down the key players here. You've got the thermal engine, your workhorse for long-range flight. The P1 motor is this super smart starter generator. The P3 motor, that's what gives you that quiet electric vertical lift. And the 800-volt bus is the electrical backbone holding it all together. But the real star of the show, it's that KO clutch. Think of it as the magic switch that can instantly change the entire personality of the propulsion system.
Now, the real genius of this system isn't just the parts, it's how they dance together. This architecture isn't static, it's constantly reconfiguring itself for every single phase of the mission. This slide really shows it well. The system has 4 distinct personalities, or modes. And the brain, which we call the Hybrid Propulsion Control Unit, is always working, always optimizing, picking the absolute most efficient mode to give the pilot the power they're asking for. So in mode A, E-Stealth, the clutch is open, engine's off. You're in full ninja mode, silent, pure electric. In mode B, Series Range, the engine kicks on, but it's just acting as a power plant, a generator feeding the electrical system. For maximum punch, you hit mode C, Parallel Boost. The clutch closes, and you get everything, engine and battery, powering the props together. And finally, for that long, efficient cruise, you've got mode D, Direct Drive, where the engine is mechanically connected, giving you this incredible, almost 98% efficiency.
So how do you actually build something this complex? Well, here's the thing. You have to throw out the rule book from pretty much every other industry. This is not like developing an app or even a car. In aerospace, the idea of trial and error, it just doesn't exist.
This right here, this is the bedrock of everything we do. So what does that actually mean? It means for a top-level requirement, say, the aircraft has to keep flying safely after a power failure, we have to be able to follow a golden thread, all the way down to the specific lines of code and the exact hardware components that make that happen. And just as critical, we have to be able to trace it back up to prove that every single line of code is there for a reason, tied to a specific safety requirement. And this is the tool we use to manage that traceability, the V model. Think of it like this. On the left side of the V, we're creating the blueprint. We break down the requirements from the entire aircraft down to subsystems, all the way to tiny components. Then on the right side, we build and test our way back up. We verify the components, then the subsystems, then the whole integrated system,
proving at each step that what we built is exactly what the blueprint called for.
And the rigor here is just absolute. For software, under a standard called DO-178C, we have to test 100% of all possible decision paths in the code. No exceptions. For hardware, DO-254 forces us to design circuits that can literally withstand a cosmic ray from deep space flipping a bit in its memory without causing a problem. I mean, the standards are on a completely different level.
All right, so we've talked about process. But what does safe actually mean in our world? It's not a feeling, it's a number. And frankly, it's a number that's almost impossible to wrap your head around.
There it is, 10 to the minus 9. That's the target, a probability of a catastrophic failure of less than 1 in a billion flight hours.
So what on earth does that actually mean? It means you could have one of these aircraft flying 24/7 for over 114,000 years before you would expect a single catastrophic failure. And this isn't some aspirational goal we'd like to hit. It's a mathematical proof required by regulators. It's the same standard a Boeing 787 has to meet. That is the price of admission to the skies, period.
And the entire system architecture is built around this principle: continued safe flight and landing. It's simple. After any single failure, the aircraft must be able to keep flying and land safely. This is where the P13's hybrid nature is such a game changer. It has dissimilar redundancy, two completely different types of energy sources, fuel and batteries. So a common problem, like contaminated fuel, can't take out your entire propulsion system.
Okay, so how in the world do you prove a 1 in a billion probability? Obviously, you can't just fly the aircraft for 114,000 years. You prove it on the ground by running the system through an absolute gauntlet of tests, moving methodically from computer models to full-scale physical test rigs.
It's a three-stage process. First, we do hardware-in-the-loop testing. We hook up the real flight controller to a supercomputer that tricks it into thinking it's flying, and then we hit it with every possible failure we can dream up. Next up is the Copperbird, a full-scale replica of the entire electrical system to test power quality and shorts. And finally, the Ironbird. This is a massive rig with the entire physical propulsion system, where we test the real-world responses thousands of times before that aircraft ever leaves the ground.
And you don't move from one stage to the next just because you feel like it. You have to hit these incredibly specific, hard, quantifiable benchmarks. For example, efficiency in cruise must be over 92%. Thrust can't fluctuate more than 5% when you switch modes. You have to prove a battery fire can be completely contained. And of course, you need the final sign-off from the aviation authorities on every piece of hardware and software. Only then can you move on.
And that really brings us to the core takeaway here. Success in this new world of aviation isn't about one magic motor or a revolutionary battery. It's about the integrity of the integrated system, the whole shebang, and the unbelievable rigor of the safety case used to prove it. From a pure engineering perspective, this is why the P13 hybrid architecture is the clear path to certification.
Because at the end of the day, all of this meticulous, obsessive engineering, it's about more than just getting a certificate. It's about building and earning public trust. It is the only way to make sure that when these aircraft take to our skies, we're not just watching a new piece of technology, but we're embracing a future that we know with mathematical certainty is safe.